Welcome to this video of RaMa-Scene on circular economy and environmental input-output methods. The circular economy is a paradigm that promises the reduction of environmental impacts and resource demand while increasing economic performances. It is composed by multiple strategies that require complex changes in the real economy. These complex changes can be simulated using models so to guide decision makers in their application. According to Aguilar Hernandez et al., the implementation of the circular economy paradigm in particular is composed by four main macro-level strategies. We have residual waste management, resource efficiency, closing supply chain loops, and product lifetime extension. Residual waste management concerns post-consumption activities where the materials are disposed of outside the economy. Landfilling, incineration, waste composting, and wastewater treatment, among others, are parts of these activities. Resource efficiency has to do with the mechanisms that optimize resource flows by using fewer resources per unit produced. For example, this happens when we are able to reduce waste and losses during manufacturing of products or their components. Closing supply chains applies to the reintegration at different levels of the supply chain of materials that are recovered after their use. The reuse of products or components, refurbishing, and recycling. These are all examples of these types of activities. At last, we have product lifetime extensions, which concerns the slowing down of resources use as a consequence of extending lifetime of products. This means that designing products and components, keeping in mind their potential longevity and improved maintenance. When countries and industries implement these strategies in the form of specific policies, and new technologies of course, they stimulate changes in economic activities, their relationships and environmental impacts. The implications of such changes are not always obvious, and they influence other sectors, as well as employment, taxation, and environmental impacts in unexpected ways. For instance, increasing the amount of secondary materials contained in a certain product might require changes on waste collection services, as well as recycling sector at large, and changes on the sector providing the primary materials. It is very important that practitioners are aware of the complexity of implementing these strategies and that they have a good understanding of tools and models that allow them to deliver such macro-level global insights. There are various economic models and tools to analyze the economy and create scenarios. In particular, we have computable general equilibrium models, regression models, stock and flow models, and input-output analysis, which are some of these instruments, but there are many more. Every one of them has, of course, weaknesses and strengths that make them more suitable for different types of analysis. In this video, we will discuss input-output analysis. In particular, we describe a version of this system called environmental input-output analysis. The input-output model has the fundamental assumption that each unit of input in a year corresponds to a unit of output. The model is linear and always balanced. Input-output data is regularly collected and organized by national accounting authorities, following the international agreed standards of the system of national accounts. In this system, we have multiple elements. We have the final demand, or how much money from household governments, NGOs, and investment is spent on specific products or services. We also have the intra-industry transactions or intermediate transactions. That is the accounting of demanded by each sector in the economy in order to carry on their own activities, as well as delivering goods and services to final demand. We also have the factor inputs. These are also known as primary inputs, which represent value added, taxes, and employment in each sector. In input-output analysis, we assign letters to each element. We have Y, which is for the final demand matrix. We have Z, that is used for intermediate or also known as intra-industry transaction matrix. And we have W, which is the factor input matrix. Each of these elements correspond to a matrix in the input-output database. From these three matrices, we can calculate multiple other objects that are useful to analyze the input-output database. We can calculate X, which is the total product output that is obtained by the raw sum of all intermediate transactions and final demand. We also have the technical coefficient matrix A, also known as direct requirement matrix. This matrix tell us the ratio between each transaction and the total product output. A very important equation that defines input-output analysis is the Leontief inverse equation. This equation results in the matrix L of the same dimensions of the intra-industry transaction table. It is also known as the total requirement matrix, and it takes its name from the Nobel Prize winner economist Wassily Leontief. This matrix shows the coefficients of the industrial inputs required to satisfy 1 unit of final demand. The Leontief inverse is given by subtracting the identity matrix I and the direct requirement matrix A and inverting the results. The Leontief inverse can then be used to calculate the total product output X by multiplying L by a final demand vector. The final demand vector is the raw sum of the final demand matrix. There are multiple reasons why one should want to calculate total product output X from the Leontief inverse and a final demand vector. In our case, it is because we want to apply changes in final demand to simulate changes in the way final consumers use products and services. These changes could have repercussions on primary inputs such as value added, employment, or on environmental extensions. Environmental extensions are vectors or matrices of environmental data on greenhouse gas emissions, extraction, land use, to just name a few. But there are many more. So if we assume we have a vector of coefficients that we call B, that was obtained by dividing a vector of environmental extensions E, and we divide it by the total product output, we can say that the E vector is a product of environmental extension coefficients, the Leontief inverse L, and a vector of final demand. Having explained the basic principle of environmental input-output, it is good to specify now that within RaMa-Scene we employ the multi-regional environmentally extended input-output database, EEIOA. Multi-regional because it includes interconnected data for a total of 49 countries and regions. Environmental extended because it contains environmental data resulting from economic activities. So we now know how the input-output model works and how it's structured. But what if we want to create scenarios? How will we do that? We have various options. We can change the way households, governments, etc. consume goods and services, and we can now do this by modifying the Y, which is the final demand. Or we could also intervene in the industrial relationships for the manufacturing of goods and provision of services, and we do this by modifying the technical coefficient matrix A. Or we could also change employment, taxation, and value added in the system by modifying the factor inputs W. Or yet again, change the emissions and the impacts resulting from a specific economic activities by modifying the extensions. Whatever you do, it is very case specific and dependent on the reasons behind these changes. These changes will need to be very well motivated, and different scenarios will require different assumptions in the way the system is modified. With this, we conclude this RaMa-Scene macro-level environmental input-output and circular economy tutorial. We hope you enjoyed it.